guys, I'm Shriram. Today we are going to see Dijkstra's algorithm on finding the fastest route in the city. Okay. Yes. Okay. Imagine you are in a smart city and your GPS needs to find the absolute fastest route from point A to point B or point A or some other point. Yes. Not just any route. Uh, the shortest one. How does it do that? uh, you can understand now. uh, yes, today we are going to answer that using one of the most elegant algorithm in computer science, that called the Dijkstra's algorithm. We have a city with six intersections labeled A through F. Roads between them have different travel times in minutes. Our job is find the minimum time to travel from intersection A to uh, intersection F, and we are going to code this in Java step by step, and so you can see exactly how the algorithm thinks and how the algorithm works. Okay. Yes. Next, wait a minute. I'm going to change the PPT. Yes, it is. Yes. First, we need to understand the graph, right? Yes. Let's understand the graph. We have six nodes called A, B, C, D, E, F, S, and roads connecting them with weights representing travel time in minutes, like 1, 2, 4, 10, 8, like that. Yes. For example, A to B takes 4 minutes and A to C takes um A to C takes 2 minutes and B to C is just 1 minute, and um, so on. Yes. In our Java code, we represent this as a 6x6 adjacency matrix as a 2D array called G. I will show that in code. Each cell G of which means graph of uh, rows and columns, which means i's and j's, stores the travel time between node I and node j. Yeah, 0 means no directed road exists between those two nodes. So g of 0 comma 1 means 4. There will be a road. It was hidden, some mistakes, sorry. 4 means it takes 4 minutes from A to B, and the graph of 0 comma 2 means 2, which means 0 comma 2 means A to C, right? That's a 2 minute. That is shown that from A to C. We set our start node as equal to 0 in code, which is A. Starting node is A, and our end node is F. Yes, F, right? Yes. And next, I'm going to, yes, see this, and you will get some stuffs. Yes, now I'm explaining this. Now let's talk about the idea behind the algorithm before we touch the code. Yes, Dijkstra's algorithm works on a simple greedy principle. Always explore the closest unvisited node first, right? Like DFS, BFS. We start with the distance array. Let's call it D. We set the distance to every node as a infinity. First of all, meaning unknown, which means unknown. Infinity means unknown. Expect the starting node A, which is 0, because we are already there. Yes, we are already starting in starting node, right? In S, which means yes, A. Then we repeat this process. Pick the unvisited node with the smallest known distance. Mark it as visited, then look at all its neighbors. If going through this node, give a shortest path to any neighbor. Update the neighbor's distance. This is called what is that? This is called a relaxation. Yes. We keep doing this until all nodes are visited, and whatever distance we have uh, stored for f at the end, that's our answer, which means that is the shortest path. That is the shortest path in the city. Yes. Now we move to code. Yes. That there. Okay. Let's now walk through the actual Java code. First, we initialize the distance array for. Okay. Wait a minute. Wait a minute. I'm checking where I need to start. Right. Yes. Now we are entered the main loop. It runs n times. Okay. Because yes. Oh, wait a minute. First we initialize the distance array. For that I am using for loop. That for int I is equal to 0, I less than n, I plus plus d of I equal to this line. We initialize that as 0 to all the nodes to 9. We use 9 as our standard in for infinity, because then we set d of starting, which means distance of starting node as 0, distance from a is itself is 0. Okay. Now we enter the main loop. It runs n times, once per node, right? Inside the loop, the first thing we do is find the unvisited node with the smallest distance. That's this inner loop. We scan all nodes, skip visited ones, and because visited ones are not needed, right? And keep track of the minimum. That is the concept I before told, right? This is our greedy choice. We always pick the nearest unvisited node. Once we have that node u, we marked it as visited, because we there is some chance visiting the same node again and again, right? For that we are we are noted that as a visited. Yes. Then we do edge relaxation. Did you remember the relaxation? Yes. The heart of the algorithm. For every neighbor j of u's, if there is a road g of u and j, and that must be not equal to 0. How can I explain? Yes. See this if, and you can understand. How can yes, if there is a road and the neighbor is not visited, right, and the new path through u is sorted, then what we are already know is the relaxation, which means then we need to update d of j equal to d of u plus g of yes. These stuffs we need to do that. That's really. Yes, after all iteration, d of e is the distance of reaching f in which means it gives the answer, right? Yes. Wait a minute. I can explain this. Yes. Let's trace through the execution using our table, right? Remember this graph, and now see the table. We start at a, distance b gets 4, c gets 2, and everything else stay at the infinity, right? And nearest unvisited is C with distance 2, which means smallest. We visit C through C, and B gets updated to 3. Yes, because uh, there is some connection in 3, right? Yes. Now B has a distance 3, and its next like through B and D becomes 8, and 8 plus 2 is uh, no, not 8 plus 2, 3 plus 5. Yes, 3 plus 5 comes 8, 8, because we back trace that root, right? Then visit D with distance of 8 through D and D update to 10, because of 8 plus 2 is 10. We are back tracing that, and becomes 4, becomes F becomes 14. That's 8 plus 6, which means E to F. I should there. E to F is 3. This is a mistake. Sorry. Yes. And visit T with distance of 10 through E comma F updates to 13. That's the 10 plus 3 is better than 14, right? Visit F for dawn. The shortest time is 13 minutes. Where the path of A to C and C to B, B to D, D to E, then F. Yes. Then I have results and some complexity of the codes. This is a Python code, and this is a example code. Don't take this as a code as right. Let's wrap up this the key points, right? Our program outputs. Wait a minute, I never showed that, right? Our output is yes, the shortest. Yes, I said the 13 minutes, and that comes there, right? So our code is working perfectly. Yes. Okay. Now I explain that. Yes. So the result is 13 A to F. Now what's the time complexity? What's the complexity of this approach is, since we are using a nested loop to find the minimum and scanning all nodes each time, the time complexity of order of v square, and where v is the number of nodes, right? Space complexity is order of v. That's not a problem at all. For the distance and visited arrays, if you need to scale this to a much large graph, you can swap the inner loop with the priority queue, which brings time complexity down to order of v plus e. That's the heap optimized version. That's their big takeaway is one, like Dijkstra guarantees the shortest path, but only when all edges weights are non-negative, and to the core idea is greedy selection combined with edge relaxation, right? Uh, and one more thing is, this same algorithm powers real world system, and GPS navigation network packets routing. Yes, route in routers. Sorry, in routers. Uh, then airline scheduling. Yes, and airline scheduling, uh, and so on. Smart cities traffic system also. This is also an example. If you found this helpful, the modifying the code, change the weights and add a new node, or print the actual path instead of just the distance. That's the best way to make it stick. Okay, and I will share this in group. uh, Thank you.